Half a day, everybody. Welcome to the notes for 1.3, which is our last section in Unit 1 about accuracy and precision. You should by now have these 2 pages at your table, which are the notes for this section. Yes, I know that there's 4 total pages, which is 2 sheets back and front, and it's quite a bit, but there's a lot of work to do with this unit, or this section rather. So I just want to make sure that we're all good in the hood before we move on to subsequent units in chemistry. The objectives or the learning targets for this particular section are very critical for you to know how to do because they will be repetitive common themes later during the course of the school year. And so being able to differentiate between accuracy, precision, be able to express accuracy, being able to tell if a digit is significant or not, and then being able to perform calculations expressing the correct number of significant figures is a very critical skill. So without further ado, I'm going to go ahead and remove my face and then we'll just have some writing being shown on the board along with my voice. So I'm sorry if I screw up along the way. This is the first time I've done this, and hopefully if I need to be out again, this will be the norm. So here we go. Let me remove my face from the screen. Okay. So looking at your notes here, we have the beginning part, which is all about accuracy and precision. Um, and oftentimes people confuse the two, thinking that they're the same, and really they aren't the same. And so let's see if I can get this screen to move over one. There we go. Okay. So scientists use different tools in different manners to reflect different levels of accuracy and precision. And a lot of times people think they are the same, like I said earlier, but they are not. So we'll go over the exact definition for each so that way you can understand what the differences are between the two. So accuracy here is the closeness of a set of measurements to the correct or the measurement to the correct or accepted value. Um, so you can go ahead and put in that word accepted there in the blank that you have in your notes. Let me move this little thing over. Okay, oops, move that there. Okay. Um, and up here on the top, you have this word that says the tools that scientists use to measure affect how accurately and precisely the measurement can be made. Okay, so like we talked about last week, right? So when you would use a beaker versus a graduated cylinder. So obviously we learned that a graduated cylinder is a lot more accurate as far as reporting a value for liquid volume than a beaker. So those two tools then would have a different level of precision contained within each one. Okay, so let's look at here. So for example, we have a quarter, right? Let's make the quarter appear. Quarter, quarter, where are you at, quarter? Okay, so there's our quarter. And we place the quarter onto a scale to determine its mass. And we see on the scale that its mass is 5.67 grams. Then if we went further to the US Mint to look up the actual mass of a quarter, let's see if this is going to show up here. US Mint, actual mass of quarter. Let's see. The actual mass of the quarter, if it wants to pop up. Okay, computer. This is not a good thing. Hold on a second. There we go. Okay, so according to the US Mint, the actual mass of that quarter should be 5.670 grams. And so looking at the definition here of accuracy, ooh, yay, wow, great stars there. The definition of accuracy is how close a measurement is to the correct or accepted value. So taking these two and comparing them with each other, we can say that this scale or this measuring tool is accurate in reporting the mass of the quarter. because the reported mass measurement here matches what the US Mint says that that quarter should weigh. Make sense? So accuracy is the closeness of a measurement to the correct or accepted value. Okay, now let's move on to precision. Oh, 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 oh. Okay, well, I guess I gotta erase all this stuff before I can move on. There we go. Let's erase, 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 erase. Okay, moving on. Okay, so how precise are your measurements? So a lot of times people use accuracy and precision interchangeably. Like I said, they're not. So if we talked up here that accuracy tells how close your measurement is to an accepted value. If the quarter weighed 5.67 grams, the accepted value was 5.67 grams. That means that the measurement made with that measuring tool, the scale, was accurate. Now the question remains, is it precise? Well, with precision, it's kind of interesting that you can't tell precision if you only have one measurement. With precision, you need to have at least 3 or more measurements made with the same measuring tool repetitively made in order to determine the precision of a measurement. So precision here is the closeness of a set of measurements, that's what goes in your blanks there, of the same quantity made in the same way. Okay. So now obviously, since if we use the same scale, we put that quarter onto the scale 3 times, we should end up with the same measurement showing up on the scale screen. But what if we use 3 different scales to measure that same quarter's mass? Well, if we use 3 different scales, let's see if it's going to pop up here. Oh, hello. Okay, so we have a scale number 1 with 1 quarter, scale number 2, second quarter. Actually, these are the same quarter, but this is a new scale here. So this is scale number 1, and this is scale 2. And then we'll have scale 3. Hello. Okay, so this is scale 3. Can we say, looking at these values here, that the scale's measurements are precise? Well, of course, looking at the numbers here, we're at 5.67, 5.80, and 5.05. We will say that those measurements are not precise because they are not close together. Okay. So there are 3 trials there. Those values are pretty spread apart, and so we can say that the measuring tool that we have in this regard is not precise. So reviewing real quick again, precision is the closeness of a set of measurements made of the same quantity in the same way. Okay, so let's erase this guy. Erase all of this. Okay, so moving on, we have 3 sets of bullseye here labeled A, B, and D. And the question is going to ask of us down here, which figure shows precision but not accuracy? So remember, precision is a closeness of those measurements to each other. Accuracy is the closeness of those measurements to an accepted or real value. So think about it for a moment. Which figure shows precision but not accuracy? So we're looking for precision is close together but not accuracy. So not close to the accepted value. So if you're thinking about a bullseye, right, the accepted value would be considered hitting the middle or the bullseye of that target. Precision then would be reflected in letter B. Okay, so these are precise because they're pretty close to each other, but they are not in the middle of that bullseye where they would then be accurate. So that is precise but not accurate. Which figure shows precision and accuracy? So we're looking close together and close to the target or the bullseye in the middle. So precision and accuracy. So which one would we say? Yes, D. I hope that you're all responding. You should respond even though I'm not there. Okay. Then lastly, we have which figure shows neither precision nor accuracy. So we're looking for the darts that are far apart and are not near the bullseye, right? So that case would be reflected over here. See how these guys are all over the place? This is kind of maybe what it would look like if I played darts. So this is going to be letter A, which is not accurate nor precise. Okay, if you need to take some time to discuss, you can pause the video here and then we'll move on to an example problem. Okay, so let me erase all these markings here so that way we can talk about the example problem. Everybody's good? Yay! All right, example problem. So we have density data collected by 3 students, and all of these measurements are made in grams per cubic centimeter. So just because you don't see units here, they're mentioned up here in the header of the table. So that is perfectly legal and a-okay. All right, so we have this table measurement. Student A made a measurement of the density of the object 3 times. Student B did it 3 times, and student C as well. So question number 1 says, what information do we need in order to determine if a student is accurate? What information do we need in order to determine if a student is accurate? So going back to your definition of accuracy, it says how close a measurement is to the correct or accepted value. So in order for us to know that, we need to know what the accepted or correct value is, right? So we need to know what the correct or accepted value is in order for us to determine accuracy. What do we need in order to determine if a measurement or a set of measurements rather is precise? Do we need 1 measurement, 2, 3, right? So we need a set of measurements made in the same way with the same instrument to determine if your measuring tool is precise. Okay. So looking at question 2 there, it says, which student's average is the most accurate? So we have the density. So this right here, this is going to be our accepted value for the object. So since we're looking for accuracy, we're looking to see which student had a average that is closest to this. Okay. So closest to that would be which student? Yes, student A. Student A's average measurement was closest to the accepted value, thereby it was accurate. Which student is the most precise? Well, in that case, what we need to do is we need to look at the ranges of the measurements that each student made and look to see which one had the smallest variance between the highest and lowest measurement. So for student A, highest was 1.60, lowest was 0.54, so the difference here is 0.06. For student B, the highest was 0.68, lowest was 0.40. So if you look at the difference there, your difference is 0.28, which is kind of a lot. And here, your lowest was 0.69, highest was 1.71. So the difference between those measurements are 0.02. So in this case, student C would be the most precise. Okay. Let's write this down here. Okay. So student C is most precise because their measurements are the closest to each other. Not necessarily close to the accepted value. That's not a criterion for precision. Precision just means, are those measurements close to each other? So the closer they are to each other, the more precise they are. Okay. All right. So let's go ahead and erase all of this. Okay, and we are moving on. Okay, so next we're going to talk about percent error, because scientists like to be objective, meaning they like to report measurements, or they like to report with numbers, right? We don't be like, oh, it's close, oh, it looks like it's good, right? We like to be able to quantify stuff. So when determining accuracy, we can report how accurate a measurement is by expressing its percent error. Okay, so this is what goes in your blank there. Okay, so we want to be able to express accuracy with percent error. It's a very simple calculation. All you need is the accepted value and the experimental value, and that will suffice. So let's go ahead and move on to what here is your equation. So all you need to do there is go ahead and copy that into the cloud. That's on the top of the back of the second page, where percent error is equal to, and keep in mind, it's the absolute value. Okay, so we're not going to have anything negative here, right? We're just looking for the difference between the accepted and the experimental value here. So what is the difference there? And then, so that way you'll have always a positive number. And that will be divided by the accepted value times 100 because it is a percentage. Okay, so it's accepted minus experimental, the absolute value of that, divided by accepted value times 100. I'll give you a few moments to write that down. I hope you're still following along with me. Okay. Let me go ahead and erase this. Okay, moving on. Here is the density data collected by 3 students from earlier. And we're going to calculate what student C's percent error was. Okay, so we can do that here if the accepted density is 1.59 grams per cubic centimeter. Okay, so on your notes though, it looks like in sample problem number 2, they're using the data from student A. So let me move that over a little bit. Okay, here we go. Okay, so for student A, we'll go ahead and do this one because that's the one in the sample problem. Okay, so we have our formula there, and let's go ahead and indicate here. First, we need an average because that's what we'll use for our our experimental value. Okay, so usually we'll calculate an average first, and then that will be our experimental value. So if you add up all of these, and by the way, the unit for this is grams per cubic centimeter. Apologies, remember we said no naked numbers. So if you add all these 3 here, divide by 3, you'll end up with 1.50 grams per cubic centimeter as the average for those 3 trials. Okay, so we'll go ahead and plug these values into our expression here. So percent error equals the absolute value of the difference between the accepted value, which is here, so 1.59 grams per cubic centimeter, minus our accepted experimental value, which is down here in the bottom left, 1.50 grams per cubic centimeter, absolute value of that, divided by our accepted value, which is 1.59 grams per cubic centimeter, all of that times 100. Okay, so I should have told you this earlier in the very beginning of the lesson, but you kind of need a calculator. So if you don't have one readily available to you at the moment, please pause the video to get a calculator. There are some in the pink basket over by the blue folders, and there are some graphing calculators as well. And at this time, you may use your phone also. So if you want to use your phone's calculator, that's okay. Also, please feel free to use a calculator over by the blue folders. Okay, but please don't just sit there, okay? I see you just sitting there. Make sure you're getting up. You get a calculator. Okay, good job. All right, so let's calculate this. You plug it in the calculator, 1.59 minus 1.50 divided by 1.59 times 100, and you get a percent error value of 5.66%. Okay, well, what does that mean? That means that this student's experimental value over here was 5.66% away from the accepted value. Okay, and obviously as a scientist, you want the lower the percent error, the better. That means that your results were more accurate than someone else who maybe had a higher percent error. Okay, so we want to try to keep percent error low, just so that way we can say that our results were accurate. And accuracy is a good thing. Okay. All right, so if you need some more time to kind of mull over this, go ahead and pause the video. If you need to, you can do another calculation for another set of students' trials on the first page. But if not, let's move on. Okay, I'm going to go ahead and erase all of this. Okay, so moving on to the next slide. Okay, so now we look at how many digits do I report, okay? So we have 3 examples here of digital scales. And I remember telling you that when we first introduced the measuring tools, that the scale that you're most likely going to use in class is like this one here, which reports to 1 decimal place. But there are digital scales that can report to 2 decimal places like this one, or even 3 decimal places like this one on the right. Obviously, the more decimal places that scale can report, the more expensive that scale becomes because of its increased level of precision. So, and the more decimal places we can report, the more precise your measurements can become, and the more accurate then as well. So let me go ahead and erase this. Okay, so it's always a good thing to be able to report the most digits as possible. So you always want to have, as a scientist, a measuring tool that can report more digits than, than your neighbor. So if we had a scale like this one over here, that one is the most desirable of the 3. But sometimes budgets and things like that are constraining factors, and in that case then we'll have to settle for something like this for use in an everyday science classroom. Okay, so moving on. Okay, so here are 2 rulers, I guess, ruler A and ruler B. We're measuring the same yellow stick. And what I want you to do is to first look at the yellow ruler, which is ruler A. And we're going to record the measurement of the yellow stick based upon ruler A. Take a look at it and report the measurement that you think is being reported there, or that you can report using ruler A. All right, so we know for a fact that this yellow stick is somewhere between 12 and 13 centimeters, right? Because it's right in between these 2 lines. Oh, let's not use that. It's right in between these 2 lines here, the marks for 12 and 13 centimeters. So we know for a fact it's greater than 12 but less than 13, right? So we know this to be certain. Now there's no calibrations or graduations between 12 and 13. So the next thing I can do, the next best thing is to guess what's going on between the 12 and the 13. Okay, so it looks like it's about halfway between 12 and 13. So I'm going to report this measurement of this yellow stick to be 12.5 centimeters. Um, this 0.5 right here is perfectly legal to report because psychology has said that the human eye is reasonably able to take a distance and to divide it into 10 equal pieces. And so we can take that 0.5 as being part of the measurement. Even though it does introduce some error, it's still accepted and reasonable error to assume. Okay. So 12.5 centimeters. Now we're not going to go any further or anywhere past that 5 or the 10th place because for us to indicate a 100th place measurement there would introduce too much error because of the lack of precision of our ruler, ruler A. Now let's look at ruler B. Ruler B here has graduations all the way to the 10th place. So for a fact, we can tell that ruler B is, for a fact, we know that it's 12.5 centimeters because the markings on the ruler told us that. Well, we can look and go just in the same way that we estimated this 5 up here. We can go one more place past that and estimate what's going on in this space right here between the 0.5 and the 0.6. Well, it looks like it's not going anywhere past that 0.5 line, so we'll just report that as a 0. Okay, so in both instances here, we have this measurement or this digit right here, which is estimated, but it is still part of a significant, still significant in terms of the part that it is reporting. Okay, so what you need to get from here is that your measuring tool, the level of precision that is indicated or that your measuring tool is telling you, is going to greatly affect your measurement as far as how precise it can be. Okay, so now moving on, let's look at the next slide here. Okay, so we have in the cloud, we're going to report all known digits plus one estimated digit. So we're going to go ahead and write that in the cloud. Oops. Let's see. Okay. So in the cloud, you're going to say that when you're reporting measurements, now there should be centimeters right here. Okay. So you're going to write down that you're going to report all known digits plus one estimated digit. Okay. Always when you are reporting measurements from whatever measuring tool you're using. Okay. So if we missed out on a digit because we did not include that one estimated digit, then you're just sacrificing some precision of your measurement, and that's not a good thing. So when you report your measurement, you're going to use your measuring tool to its full capacity and report every known digit the instrument told you plus one estimated digit. Okay, so in these two cases right here, the estimated digit is this 5 right here and this 0. Okay. All right. So let's see, moving on. Let me close this up here. Okay. So this leads us to significant figures. So just like the word significant means, it means important, right? A figure in this case means a digit in your measurement. So a significant figure is a digit that's meaningful in terms of accuracy or precision, and it carries meaning for that measurement. Okay. If a figure is not significant, then we're not going to really care what it's doing. That means it's not telling you, it's not reporting any type of meaningful measurement. Okay. And I'll tell you right now that most digits in measurements are significant. There are just a few that are not. And it's usually those few that are not that's going to cause a lot of strife for people. But it's not that difficult. And the only time you'll need to wonder, is a digit significant or not, is if it's a 0. Okay. So let's go ahead and go to the second page. Let's see. Okay, here we are. Okay. So looking at this picture here, we have, remember we said earlier, you're going to report all known digits plus one estimated digit, right? So looking at this pencil in terms of recording its measurement, We know for a fact that it's falling right there, right? And so it's bigger than 6 centimeters, but it's not yet 7. So this 6 right here is a known digit. That's known, right? And what we're doing now is we're going to estimate what's going on between the 6 and the 7. It looks like it's more than half. I'd even say more than 0.6. So let's just go ahead and go with 0.7. So 6.7, even though this 7 is estimated, it's still significant because it is important as far as reporting the measurement of that pencil. Okay, so this measurement here, 6.7 centimeters, has two significant figures, the 6 and the 7. Okay, so let's move on. Just to remember that remembering the ruler from the yellow stick, right, or the yellow stick measurements, 12.5 centimeters is not the same as 12.50 centimeters as far as precision is concerned, okay? So you might argue and say, oh, but it's the same. No, it is not the same. Remember, in science, we use measurements, right? So if these were just numbers, 12.5 and 12.50 without a unit, then yeah, okay, the reason could say, but the reason why they're not the same is because there's nothing reported here in this hundredths place. So because it's not reported, that means that we don't know what it is, right? So if we don't know what it is, we can't assume it is going to be a 0. In this case, we can record this 0 because our measuring instrument was marked in such a way that this 0 here is going to be our estimated place, which is part of our reporting of measurements. And over here, in the first measurement here, the reason why we can't say 12.50 is because our measuring tool was not marked in such a way to allow us to report to that hundredths place. So the last digit that we can report here in this case would be the tenths place, and that then remains to be estimated, okay? So please make note that these two are not the same as far as precision goes. Okay, moving on. Okay, so this little schematic here is in your notes there. It goes over which digits are significant, which ones aren't. So we have leading zeros, we have in-between zeros, or we like to call them sometimes the sandwich zeros. We have non-zero digits, which are numbers from 1 to 9, and then our trailing zeros, which are zeros at the end of the number. Okay, so it's not too difficult if you just remember what the words mean. Okay. So here we have, after you have taken a measurement and written the correct number of digits, you often need to do a calculation. The calculation has to communicate the same amount of precision, okay, as the original measurement had. We cannot, okay, can't write and talk sometimes. Okay, we can't, what was I about to say? I lost my train of thought. Oh, we can't use you can't have a measurement that is more or less precise than the measurements that it came from. So for example, if we're going to calculate density, which involves math, right? Usually when you divide mass by volume, your calculator ends up giving you something that's like 5.24967, da, 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 da. So if we were to report that, obviously that's going to be a very precise measurement, so much so that it becomes erroneous, okay? So what we need to remember to do is be able, and we'll learn this in a minute, is to round our answer to reflect and have the same precision as our original measurement, which would be mass and volume, okay? All right, so this little schematic here is in your notes. It's also on your reference sheet, so for you to remember how to count a digit as far as it being significant or not, okay? So the first thing we have are all digits 1 through 9. They are always significant, always, okay? So in this example here, with the 5.96 in the green box on the top, this guy right here, 5.96, and for the sake of argument, we're going to assume all of these are measurements and they have units on them, okay? But just to kind of keep things short, we're just going to take the units off. So for right now, let's just assume all of these are measurements with units, okay, but they're just not indicated. All right, so all of these here, these 5.96, there are no zeros there. They're all non-zero digits, so those are reported measurement. 5.96, we have 3 significant figures in that measurement. Okay, next. Leading zeros. Those are the zeros in front of a measurement. So like this and this, okay? That means the measurement was so small that it did not start in this example's case until the hundredths place, which is right here at the 5. So in that case, we have to hold the place value with something, right? So we're holding it with a 0 there. But that 0 really isn't reporting any measurement. It's just holding the place value. So if it's a leading 0, meaning the measurement was so small, smaller than 1, and you have those zeros that are holding a place, they will not be significant. In this case here, 0.059 only has 2 significant figures, the 5 and the 9. So leading zeros, those are the zeros before a number that is smaller than 1, are never significant due to the fact they are just holding a place. Okay, they're not reporting measurement. Okay, next. Captive zeros. Okay, so captive zeros, just like the name implies, are the zeros that are sandwiched between digits that are not zero. So for example, this 0 right here, that is a captive 0. And the reason why those guys are significant is because they are taking place in reporting measurement. If you have a 5 in front and followed by a 0 and a 9, that means you took measurement in the beginning, you took measurement at the 9, even at the 6. So what leads you to say that there was no measurement at that 0? That 0 is measured, so thereby it is significant. So in this case, we'll have 4 significant figures, okay? So really you can just remember the captive 0 rule, or you can remember the whole intent of counting significant figures is that 0 taking place in a reporting measurement? In this case, it is. So we have 4 significant figures here in 5.096. Okay, trailing zeros. So trailing zeros are zeros at the end, and in this case, if we have a decimal point, okay? Those are zeros at the end of a number after a decimal point. So think about it this way. Remember we said if a 0 is not measured and if a digit is not measured and we put it there, that's erroneous. We're being introducing too much error there. Now, if a 0 is measured and we put it there, that means it's there. It means we measured it, okay? So in this case here, those zeros are significant. So there are 3 significant figures here in 5.00. If we just said 5, then that would only be 1 significant figure, okay? But by us saying 5.00, we're saying that this measuring tool that allowed us to make that measurement was so precise that we made that measurement down to the hundredths place, okay? Versus a measuring tool that only allowed me to make a measurement of 5 was not nearly as precise as the measuring tool that allowed me to make this measurement of 5.00. That is why those 2 zeros are significant. Okay, then lastly, we have our trailing zeros if there is no decimal point. Let's see if I can move this guy. Okay, so if there's no decimal point, our trailing zeros, like an example of 500, in that case, that's kind of the opposite of this situation over here, okay? These zeros here are holding a place, but they are not reporting any measurement. All they're doing is holding a place. So in that respect, this number here would have only 1 significant figure. Now, if I were to say 500 point like that, by adding that little tiny simple decimal point, that is telling you, hey, these 2 zeros right here are measured, this one and this one. Okay, so 500 point is 3 significant figures, but 500 without a decimal place is only 1. Okay, now when would you ever report a measurement like that? Never. but it's nice to know what effect that decimal point has. You would probably report something like this, right? More so than something like this guy, okay? And in this case here, how many sig figs would this one have? 4, yay! Okay, so this one is 4 sig figs down at the bottom. All right, so now that we went over the rules, we are going to do some practice. Okay, here we go. Okay, so here's the practice on your sheet. So we have 72.3 grams. How many significant figures do you have here? Good. All of them are significant because they're all not zeros. Okay. 60.5. How many significant figures do we have here? This zero is, this is not a leading zero, right? Oh, we're missing the, oh shoot, these are mixed up. Oh well, never mind. They're all mixed up. So this is 60.5. How many significant figures do we have here? 1, 2, 3. This is a captive zero. That means it's in between two non-zero digits. So it is significant by default. So therefore, there are 3 sig figs here. By the way, the fast way to say significant figure is sig fig. Okay. This next one here, 0.0253 grams. So these, what are these called? Those zeros, those are called leading zeros. So these guys here are not significant because they are just holding a place. They are not part of reporting measurement. So in this case, how many digits would I have here? How many of these would be significant as a measurement? 3! Yes, so there's 3 significant figures here. And lastly, we have 3 measurements made in that box on the bottom, 6.200, 620.0, and 6,200. So only difference here is the decimal is moving around. So according to my rule about zeros at the end of a number, if they are at the end and you do have a decimal point, yes, they're always significant. So this will be 4 sig figs. Here, again, I got a 0 and I have a decimal. So again, this will be 4 sig figs as well. Here, I don't see any decimal place. So the 6 and the 2 definitely, but these these zeros right here are both holding a place. They are not significant at all. So thereby, this one only has 2 sig figs. Okay. Good. Let's do more practice. Here we go. Oops, 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 oops. Oh, here, let's make my eraser. It's there. Okay, so let me move my cursor around. Okay. How many sig figs do we have here? We have 508.0 liters. So we know for a fact that 5 and 8 are significant. Only questions about these zeros. So this 0 right here is captive. This 0 right here is a trailing 0, and there is a decimal place present. So thereby, all of these are significant. So we should say 4. This next one, go ahead and take a look at that and see what you can come up with. If you said 7 significant figures, you are absolutely correct. Good job. How about this next one? Ooh, that's a little bit difficult. It's written in scientific notation. If you have a number written in scientific notation, the rule of thumb here is you only pay attention to this guy. Okay, don't look at the exponent because all that's doing is just moving your decimal around and adding insignificant zeros. So we're only going to look at this part right here, the M. Remember the part that's bigger than 1 but less than 10? That is what's going to determine your significant figures. So in this case, I have a captive 0 right here, and then I have 2 trailing zeros here, and I also have a decimal place. So that means that those trailing zeros are significant. So there's 1, 2, 3, 4, 5 significant figures in this number, or measurement rather, that is in scientific notation. Okay, let's go next. Okay, so looking at the rules, okay, so some rounding rules for you. So the rules are stated on your notes, right? So if the digit to the immediate right of the last significant figure is less than 5, do not change the last significant figure. Okay, that means you leave it be. So just regular rounding rules you've learned since you're in elementary school. If the number to the immediate right is greater than 5, then you're going to round up. Okay, so there's some examples there that are in the slide. Let's see if I can get, okay. So let's round this to 3 significant figures. Again, we're just going to assume for the sake of the slide that there's a measurement here, that there's units. Okay, so we're going to round to 3 significant figures. So 3 significant figures, you're going to start from the left and work your way right. So the first significant figure is here, second significant figure is here, third significant figure is here. That means we want to be able to cut our number off there at that 3. So we're going to look at the neighbor, which is a 2. So that is less than 5. So that means that that 3 will stay a 3 and then everything else goes away. So this is going to be rounded as 2.53 if we wanted to round this to 3 significant figures. Okay. Oh, that's already done. How about that? Hey, I almost wrote it in the same exact place as the type stuff. Hey, let me go and erase that. Okay. We'll look at the next one if we want to round that to 3 significant figures. So first, second, third significant figure is right here. Neighbor is a 6. So that's higher than 5, obviously. So we're going to round that 3 to a 4 and be reporting this as 2.54. Okay. And then if this neighbor is a 5, then we're just going to go ahead and stick with rounding up. There's some specific rules about if the neighbor is a 5 that are a little tricky, but we won't need to worry about those too much. We'll just say 5 or higher rounds up, less than 5 stays. Okay, so let me go ahead and show you that. Okay. So again, if you have any questions, please feel free to pause the video. The next part here is rounding all numbers to 4 significant figures and then rounding those to 4 sig figs as well and writing in scientific notation. Okay, so let's do this example here. Rounding the numbers to 4 significant figures. Okay, so 4 sig figs for this number is 1, 2, 3, 4. The 4th significant figure is right here. Okay, so I'm going to look at the neighbor, which is a 6. Let me move that. Okay, so my neighbor is a 6. So that means what's going to happen to that 2? What? Yeah? A what? A 3! Okay, so it's going to turn into 4.933 kilograms. Okay. Let's look at this next one. We want to round this to 4 significant figures. So 4th significant figure is here at the 9. Neighbor is a 1. So that means that 9 is going to do what? Stay or go up? Yes, it's going to stay as a 9. So we're going to say 8, 4, 7, 9. Now, do we just leave it like that? Or do we have to put something in the ones place in order for us to hold the original intent of the place value? Hopefully you said it was the second thing. So yes, we have to put a 0 here in order to hold the original intent of the place value. Because if you look at this guy, this is 84,791, right? So if we wanted to report only 4 sig figs and you just did this, you just chopped your number down by a power of 10, which is not the same as the original intent, right? So we're going to report 4 significant figures, but use a 0 in the place of that 1. Remember, the 0 here is not significant because it is a trailing 0 and there are no decimal places anywhere. So that is a perfectly fine placeholder 0 to stick there, and it is not significant. Okay, so let's do these 2 down here. We're going to round these guys to 4 sig figs and write answers in scientific notation. So remembering that these zeros here do not count as significant. They are leading zeros, which aren't part of the original measurement. They're just holding a place. So the measurement begins actually right here at the 5. So this is 1, 2, 3, 4. So I want to round to this place value. The neighbor is an 8. So that means that I'm going to round this 1 to a 2. So keeping with the original intent of the place value, let me go ahead and write this out, and then I'll change that number into scientific notation. So 5, 4, 8, 2 grams. Okay, so now let's change this into